Hello, this video is about how to write proofs by induction with sequences. Please have a bit of paper and a pen so you can pause and work things through as we go. Here's a sequence. What's the rule for getting the next term from the previous term? Yes, you double and add 1. Un plus 1 is 2un plus 1. You might recognise this as the number of moves needed to move n discs in the Tower of Hanoi. To move n plus 1 discs, you have to move the top n, then you move the bottom one, then you move the top n again. So that's good for small numbers, but suppose we wanted to find out what the number of moves was for 100 discs. We don't want to have to go through doubling and adding 1 100 times. It would be good to have a direct formula which will tell us how many moves. So we can look at this and see if we can guess one. Can you guess one? I guess u to the n is 2 to the n minus 1. That works. 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1. The proof by induction is going to tell us whether it's true not just for these small numbers but for all numbers. Okay. We've got a claim which is that if u1 equals 1 and un plus 1 is 2un plus 1 for all n, then un is 2 to the n minus 1 for all n. We are going to prove this by induction. There are 2 steps, but we can do in either order. We do step 1 first because it's easiest. Do you know what step 1 is? Yes. Step 1, prove for n equals 1. Okay, so we put 1 into there. Get 2 to the 1 minus 1, which is just 1. Is that equal to 1? Yes. We can write the Helmholtz stop to show that we've finished step 1. Okay, can you write down what step 2 will be? How it will start? Yes, step 2 is prove true for n equals k plus 1 if true for n equals k. Right, at this stage we only know it's true for n equals 1. What we're doing at step 2 is proving that if it's true for 1, then it must be true for 2, then it must be true for 3, then it must be true for 4, then it must be true for 5, and for every number you can get by keeping on adding 1, which is all the numbers there are. So step 1 and step 2 together will prove that this claim is true for all n. Each step by itself proves nothing very much at all. The 2 of them together prove everything. Right, so what we've got to prove in step 2 is that uk plus 1 is equal to 2 to the k plus 1 minus 1. It's this claim with k plus 1 plugged in instead of n. And what we've got to go on, or suppose for the sake of argument, is that it's true for n equals k, and that means that uk is 2 to the k minus 1. The other thing we've got to go on is this. We know how to get u to the k plus 1 from uk. So let's use that. The other thing we've got to go on is 2 to uk plus 1. Right, now if we assume it's true for n equals k, we can replace this uk by 2 to the k minus 1, and we will get u to the k plus 1 is 2 times 2 to the k minus 1 plus 1. 2 times 2 to the k is 2 to the 1 times 2 to the k. When you multiply powers, you add the indices. So that's 2 to the k plus 1, minus 2 add 1. Minus 2 add 1 is minus 1. But that is exactly what we wanted to prove. So we've proved it for step 2. And now there's one more thing left to write. What is it? We have to write, therefore, true for all n by induction. What we do with that last line is tell the reader we're bringing together step 1 and step 2. Neither of them proves very much by itself. Together they prove